Hello students. So I hope from the previous video session it is clear what do you understand by radial basis function and radial basis function networks. So in today's session we will be taking a numerical on radial basis function. So the university questions that have been asked pertaining to radial basis function are: draw and discuss the structure of radial basis function network, how radial basis function network can be used to solve non-linearity separable pattern. This part we will be seeing with the help of a numerical which will be explained in this video. Explain radial basis function with example. So let us go to the numerical. So the question goes like this: construct an RBF pattern classifier such that 0, 0 and 1, 1 are mapped to 0, that is class 1, and 1, 0 and 0, 1 are mapped to 1, class 2. So basically we have got two classes C1 and C2, and the 4 points, data points, are mapped in these two classes. So this is the graph that is given to us. That is, when we plot this we get 4 points and we are expecting this to be the output, mapped to 0 and mapped to 1. And this is basically for XOR function. Now, the first step is to randomly select the centers. So we are denoting our centers with mu1 and mu2, and we select 0, 0 and 1, 1. Activation function of the hidden neuron is given by. Now, as I told you, we have got one input, the hidden layer, which is nothing but where the radial basis function is used, and we get the desired output. So here the activation function of the hidden neuron is given by, so we denote it by phi of your x, which is nothing but exponent of your minus m1 upon d square max within your double bars x minus mu I square. M1 is the number of centers because we have taken over here mu1 and mu2 to be two centers, so its value is going to be 2. And Dmax, if you remember in the previous session also I told you all, is the distance between the 2 points in space or 2 centers. So the formula to calculating is nothing but square root of x1 minus x2 square plus y1 minus y2 square. So substituting these x1, y2 values, you will be getting the value of D max to be 1.414. So D max is 1.414. D square max is approximately equal to your 2 because square root of 2 is 1.414. So because we have taken two centers, we will be having phi 1 of your x, which is exponent of minus m1. m1 is 2 and d square max is also 2. So that will be deduced or deducted to 1 within your double bars x minus mu1 square. And similarly we will be having it for mu2. So the only difference here is mu1 and mu2. Now if you see your AND function and OR function for the given data points, they are linearly separable. We can have a decision boundary that can segregate both these points. For x1 and function when you apply with x2, and for x1 when you apply or function with x2. So they are linearly separable. But when you consider XOR, we are interested in XOR, so it is not possible to draw a line that can classify both these classes or the data points distinctively. So they are linearly inseparable. So we will be solving this problem with the help of RBF, that is radial basis function. And for this linearly inseparable problem, we will try to come to a conclusion how we can achieve linear separability. So if you see, this is nothing but applying XOR table. So if you see the XOR table, the inputs are 0, 0, 0, 1, 1, 0, 1, 1, and these are the outputs 0, 1, 1, 0. But with this output, we are not able to achieve linear separability. So we are supposed to get this particular output 0, 0, 0, 1, 1, 0, 1, 1. For this, we are expecting these values to be the output, and when you plot these values on your graph, we are able to achieve a linear separability. So this is how it will look when we plot phi 1 of your x and phi 2 of your x, 0, 0 when we consider, and the output is 1, 1. For 0, 0 as the input, the output is 1, 1. For 0, 1, it is 0.36, 0.36. And for 1, 0, 0.36, 0.36. And for 1, 1, it is 1, 1. So if you see 0, 1 and 1, 0, 0, 1 and 1, 0, they fall on the left hand side of the decision boundary, and your 0, 0 and 1, 1, they lie on the upper side of the decision boundary. So this is how a linearly inseparable problem can be solved to a linearly separable problem by applying radial basis function. That is why this graph is called separation using radial basis function. Now you must be wondering how these values have been obtained, because we know these values are not leading us to a linearly separability, and these values are able to provide linear separability. So I'll show you how these values are calculated. So for getting this figure, that is this particular figure, the points can be calculated using the following equations. So we consider phi 1x is equal to exponent of minus your within double bars x minus mu1 square, and phi 2 of x to be equal to exponent of minus within your double bars x minus mu2 square. We know we have considered mu1 and mu2 to be 0, 0, 1, 1. These are the two centers that we have assumed. Now we consider the first point, which is 0, 0. Now for this we are supposed to get 1, 1 to be the output. So what are we doing? Phi 1 of your x is exponent of minus within your double bars x minus mu1 square. So how do we calculate x minus mu1? We know x is our input, so it is 0, 0. And mu1 which is there, we are considering the transpose of it. So it is, this was column wise, now we write it as row wise. And what happens in that case is, when we perform the subtraction, we get 0. So ultimately what will happen in this case? This entire thing becomes 0, and e raised to 0 is equal to your 1. And that is why we get the output over here to be 1. Similarly, for the second part, the same procedure is followed. Instead of 0, 0, we will be using 1, 1, because we have chosen a center to be 1, 1. So here also we get for phi 2 of x the value to be 1. Now let us consider the second input, which is 0, 1. We'll consider this. So same formula is used. Phi1 of x is equal to exponent of minus within your double bars x minus mu1 square. Now x minus mu1, we know the x value is 0, 1 and mu1 is 0, 0. So what happens in that case? We are basically getting 0 into 0 minus of 1 into 0. So 0 into 0 is 0 minus your 1. So what happens in this case is you get the answer to be as minus 1. So exponent of your minus 1 is nothing but 0.3678. So 0 minus 0 and your 0.3678. So similarly, when you do it for mu2, the same thing is used except for 0, 0. Now the value is going to be 1, 1. So we get 0.3678. So in a similar manner, you can do it for 1, 0 and 1, 1 and you get these values. So the plot is now reduced to a higher dimensional space and is made between phi1 and phi2. So instead of x1 and x2, we have now reduced to a higher dimensional space. And that is why we are able to get this decision boundary, which leads to linear separation. So the output layer is trained. So whatever value we have got of this phi1 and phi2, it is trained using least square algorithm. Yes, which is a gradient descent technique. We have already seen gradient descent method in our previous modules. So what is done is basically whatever x1, x2 values are there, from there we apply radial basis function and obtain phi1 and phi2. And this phi1 and phi2, which are the outputs, are now given to your output neuron. But before that, the parameters like weights are added to train the model. And once the weights are added, we get the final value, that is by applying the gradient descent technique. So this is how the problem of linear inseparability that we were facing in XOR function can be deduced to linear separation by applying radial basis function. Thank you.